Hello students, good morning. Today we will discuss about the axial magnetic field produced by a current in a circular loop. Suppose this is a circular loop. O is the center of this circular loop and R is the radius of this circular loop. I is the current passing through this loop. This is the direction of current shown here, and we have to find the magnetic field at a point. Magnetic field at a point on the axis of this circular coil. Suppose this is a circular coil and this is O is center. And the axis of coil, that is line passing through this center, that is we can say that this is the axis of the coil. This coil is in XY plane. This is the X axis, this is the Y axis. Coil is in XY plane and the axis of this coil is along the Z axis, that is Z axis is perpendicular to Y axis and X axis. We can observe this by a circular ring. Suppose this is a circular loop and this is the center of this loop and this is the axis or line passing through the center of this loop. This is the axis and we have to find out a magnetic field on this axis at a point P. Suppose P is the point on this axis and here we have to find out the magnetic field due to a current in this circular loop. Now first at all we will consider a small length dl of this circular loop. We have to consider the small length of this circular loop, that is a dl. Then the magnetic field produced due to the current passing through this small length or small element dl at this point is given by the dB. The small length or small element I is the current passing through this element, and due to this small element a small magnetic field will be produced at this point P. And here we have to find out a total magnetic field at this point. Then we will find out we will consider a number of small elements on this loop. Suppose this is one small element, then exactly opposite side here is also the small element. Then we can consider another small element at here, then here, at here, and then we can take integration of dB to find the total magnetic field at point P due to all the small elements. Then total magnetic field can be given by the integrating the magnetic field produced due to the small element at point P. Now suppose magnetic field is produced at point P, then the direction of magnetic field, we have to find the direction of magnetic field. Then the direction of magnetic field can be find out, that is this direction is always perpendicular to, or it must be perpendicular to the length element and the position vector. Where we have to find the magnetic field, that is the distance from this point to small element dl. Here r is the distance of point P from the small element dl, and this magnetic field produced at point P is perpendicular to r and dl. Magnetic field produced at point P must be perpendicular to dl and r, and therefore we can show the magnetic field, that is dB, produced due to current in the small element dl is shown here, dB. Now, how can we consider this direction, or how can we find out this direction? We can use here. Suppose this is the circular loop and this is circular loop. We can consider a small element on this circular loop. Suppose this is the small element or length element of this circular loop. As this type, then this is the distance of this dl on the axis of this coil here, and the magnetic field will be perpendicular to this small element as well as this r. Then we can find out this as like this, as like this. Then we can consider here, this is the small element dl, this is the direction of r, and this is the direction of magnetic field, as like this, and this dB. So here dB is in this direction shown here. As well as when we consider a small element on the loop on another side, we will get the dB in this direction. We can show here this. Then the components of this dB, there are the components of this dB, that is, one component is along the z axis, that component is said as a dBj, or this component is equal to, we can find out, then the another component which is perpendicular to this dBj is said as the dB perpendicular. This component of dB is along the z axis, and the another component is perpendicular to the z axis. Therefore, this shown here dB perpendicular. Here we have considered a theta angle between r and the radius of the circular loop. This is the angle theta. Therefore, this is the angle of 90 degree between the axis and the radius. It is always 90 degree. Therefore, this angle becomes 90 minus theta. We can say this is a 90 minus theta. Then this dB perpendicular is perpendicular on the z axis. Therefore, this angle becomes 90 degree. Therefore, this angle, this is 90 minus theta. Therefore, this will be the theta. And the direction of dB, the direction of dB is perpendicular to this r. Therefore, this becomes a 90 degree. This will become 90 degree. This angle is theta. Therefore, the remaining this angle will be 90 minus theta. 90 minus theta. Now, we know that the dB perpendicular is perpendicular to z axis. Therefore, this angle is 90 degree. This is 90 minus theta. Therefore, this angle becomes a theta. This angle becomes theta. Now, the component dBj can be written as this dBj. This is the angle theta. Therefore, this side becomes the dB sin theta. This side becomes dB sin theta. This side is parallel to this side, or the dB perpendicular, that is the component of dB. dB perpendicular will be equal to dB sin theta. And the dBz, which is along the z axis, this will be equal to dB cos theta. The component along the z axis of dB will be dB cos theta. When we consider another small element which is exactly opposite side of this element dl, and current in this small element is opposite here shown, then we can show the R here as like this. Then we can find out the magnetic field due to the small element, that is dB, will be in this direction. Then component of this dB will be as like this, component will be dB sin theta, and this component will be dB cos theta. That is, when we consider another small element, then there are the number of dB cos theta, component dB cos theta, which are in the direction of z axis or along the direction of z axis. But dB sin theta at every point when we consider an element, then opposite dB sin theta will cancel here. This is the dB sin theta, this is dB sin theta. This dB sin theta will cancel with this dB sin theta. Therefore, the total magnetic field will be considered along the z axis, that is the dB cos theta. The number of component of dB, that is dB cos theta, which are along the z axis, will be added, or we can take the sum of all these elements, and then we can find out the total magnetic field at the point P. Now, first attempt we will use the Bow-Servot law, that is Bow-Servot law. Bow-Servot law. What says the Bow-Servot law? The magnetic field produced at point P from a small element dl is given by vector dB is equal to mu naught upon 4 pi I dl cross r upon r cube. Then the magnitude of this equation can be written by mu naught upon 4 pi I dl sin theta. But theta is the angle between the dl and r. This is the direction of current, and this is the position vector. This will be the angle between the direction of small element and the r. Therefore, this angle is of 90 degree. Therefore, we can say here sin 90 into r, I dl into r, sin 90 upon r cube. Therefore, this can be written mu naught upon 4 pi. Sin 90 is equal to 1. Sin 90 is equal to 1. Therefore, I dl upon r square. That is, magnitude of magnetic field dB is equal to mu naught upon 4 pi I dl upon r square. Sin 90 is equal to 1. The small element, the angle between the small element and this r is 90 degree. Therefore, we can say that the sin 90 is equal to 1. Now, from this figure, the r is equal to or we can say the r square is equal to, this is the angle 90 degree by the Pythagoras theorem, r square is equal to z square plus capital R square. So here from figure r square is equal to z square plus capital R square. We can put this value in this equation, then we get dB is equal to mu naught upon 4 pi I dl upon z square plus R square. Z square plus R square. Now here we know that these components cancel to at each other and the component dB cos theta will be added at each and every point when we consider a small element at a different point on this circular loop. Therefore, for the total magnetic field, to find the total magnetic field, we can here consider or we can find out the total magnetic field by integrating the dBj. Therefore, dBj is equal to, we know that dB cos theta. dBj is equal to dB cos theta. Then we can find out the total magnetic field at point P by integrating this equation. Therefore, Bj or magnetic field along the z axis is equal to integration of dBj. That is, we can say the integration of dBj is equal to dB cos theta. dB cos theta. Now we can put the value of dB in this equation. Therefore, this will become mu naught upon 4 pi I dl upon z square plus R square into cos theta. Put the value of dB from this equation 1, we can say equation 1 here. Then we get dB is equal to mu naught upon 4 pi I dl upon z square plus R square. Cos theta will be as it is. Now in this equation, the cos theta is equal to, from this figure, theta is the angle, then cos theta can be find out, that is capital R divided by small r. Cos theta is equal to this capital R divided by small r. Therefore, we can write here cos theta is equal to capital R divided by small r. Small r, here we have find r square is equal to z square plus R square. Therefore, r is equal to under root of z square plus R square. Therefore, we can put here r is equal to under root of R square plus z square or z square plus R square. Now we can put the value of cos theta in this equation. Therefore, we will get the magnetic field along the z axis is equal to, we can take this mu naught upon 4 pi I out of the integration, then this dl upon z z square plus r square. The value of cos theta is r upon under root of z square plus, here the small r, not here, here is the capital R, that is we have put the value of dv in this equation, therefore this is not small r, this is the capital R, therefore this will be r square and this will be r square. Then we can write here mu naught r, we can take the r out of integration upon 4 pi. Then you can write here dl upon this z square plus r square, root of z square plus r square is equal to, you can write here z square plus r square raised to 1 by 2. Now we can write here the magnetic field along the z axis is equal to mu naught r upon 4 pi. Then we can write here dl upon z square plus r square raised to 1 by 2. Sorry, here this 1 by 2 plus 1 is equal to 3 by 2. Therefore, dl upon z square plus r square raised to 3 by 2. Then we can take this z square plus r square raised to 3 by 2 integration of dl. Then we can write here the integration of dl means all considering this all small element along this dl plus all the small elements of this circular coil. That is, we can say thus all the small element of circular coil or sum of all small elements of the circular coil is equal to length of this circular coil. Therefore, we know the length of circular coil is equal to 2 pi r. Therefore, integration of dl is equal to 2 pi r. Therefore, we can write here this pi will be cancelled. Then mu naught r, this r into r will be r square upon 2 pi z square plus r square raised to 3 by 2. That is, this is the magnetic field. This is the magnetic field produced at point P due to the current in the circular loop. By using this equation, we can find out the magnetic field. This is the magnetic field of due to current I in the circular loop of radius r at point P. Okay, thank you.